I now want to introduce the two other rules, the sequencing rule and the conditional rule. So the sequencing rule just says, if given P, you run S1 and then Q holds, and then separately, if Q holds and you run S2, then R holds after the code has been run, you can daisy chain these two things together to get, given precondition P, if you run the first bit of code and then run the second bit of code, you get postcondition R. So that's clear here in this example. So in this example here, I've got if A is equal to 1 and B takes on the value of A, then B is equal to 1. That makes sense, and you can prove it one-liner using the assignment rule. B is equal to 1 and C takes on the value of B, then C is equal to 1. So it stands to reason by the sequencing rule, if A was equal to 1 to begin with, and then B takes on the value of A, and then afterwards C takes on the new value of B, which was A, then we're going to get C is equal to 1. We can prove that by sequencing these two lines together. So sequencing of what allows us to stitch multiple bits of code together. The other rule I want to talk about is the conditional rule. And the conditional rule is what gives us the ability to branch. It's what gives us if statements. So the conditional rule makes a lot more sense when read backwards. If you want to prove this statement here, then it better be the case that these two statements here are true. So with precondition P, if B is true, then run S1. And if B is false, then you run S2. And in either case afterwards, Q has to hold. So to prove this statement here, we have to obtain these two smaller statements. We have to obtain if P and B were true, then take the first path, and then Q holds. Otherwise, if P and not B were true, you'll take the second path, and then Q still needs to hold. So again, this rule is a lot easier seen backwards. So suppose I wanted to prove this statement here. I wanted to prove for a precondition of true, that's the weakest possible precondition, telling us nothing. If x is strictly greater than y, then assign m to be x take y, else assign m to be y take x. We want afterwards that m is greater than or equal to 0. Which makes sense, right? If x is strictly greater than y, x take y should be positive. Otherwise, if this is false, then y is the bigger number, then y take x should still be, when I said positive, I really should say non-negative. Y take x should still be non-negative, therefore m ought to be greater than or equal to 0. So if we wanted to prove this, we have to prove two things. I've highlighted each of the terms, the precondition P, the condition B, the first bit of code S1, the second bit of code S2, and the postcondition Q. So what are the two things I have to prove this statement? Well, from the conditional rule, the first thing I have to prove is P and B, so true and x greater than y. The first bit of code, m is assigned to be x take y, and the postcondition, m is greater than or equal to 0. What's the second thing I have to prove? I have to prove true and it's false to say x is greater than y. The second bit of code, m is assigned to be y take x, and then the same postcondition. So if I can prove both of these lines, then I can prove this line here by connecting them together with the conditional rule. How do you prove these two lines? Using all the other rules for whole logic that we've seen before. Okay? So we'll go through this proof together.